In this videotape, we're going to be studying implicit differentiation. Now, in all of our earlier videotapes on differentiation, y was given to us explicitly as a function of x. For example, y equals x cubed plus 4x squared plus 7. Y was given to us explicitly as a function of x, that is, y equals some function of x, and we were asked to find dy dx, or the derivative of y with respect to x. And for example, in this case, derivative of y with respect to x was 3x squared plus 8x. Y was given explicitly as a function of x. Now, suppose I give you an equation involving x and y. For example, x squared plus y squared equals 4. Here, y is not given to you explicitly as a function of x. We have an equation involving x and y. Now, we can solve for y explicitly as a function of x, and we would get that y squared equals 4 minus x squared, or that y is plus the square root of 4 minus x squared, and y is minus the square root of 4 minus x squared. Y is plus or minus the square root of 4 minus x squared. So we started with this equation involving x and y, and from that we saw that hiding inside this equation were two functions of x. Y was defined here as two different functions of x. So we say that this equation defines y implicitly as a function of x. Okay, and we see actually there are two different functions of x involved. If we sketch this curve over here, x squared plus y squared equals 4. We have a circle with center at the origin and radius 2. And of course, this is not the graph of a function because it fails the vertical line test. For every x, there should be one and only one y. If we draw a vertical line, we pick an x value, we see there's more than one y value. What we have over here is we've broken up our circle so that we have y equals positive square root of 4 minus x squared. This is the top of the circle. This is the upper semicircle here. And we have y equals the negative square root of 4 minus x squared. This is the lower part of the circle. So this is the top half of the circle when y is a positive square root. When y is a negative square root, it's the bottom half of the circle. Now, each of these is a function of x. It would pass the vertical line test. The whole circle together was not a function of x. But we saw that we could break it up so that we have the upper part and the lower part, each of which is a function of x. This is y equals the positive square root of 4 minus x squared. Y equals the negative square root of 4 minus x squared. Now, if we wanted to find dy dx, we could first solve for y explicitly as a function of x, and then find dy dx using the procedures we learned for differentiating a function to a power, because this is 4 minus x squared to the 1/2 power. However, what we're trying to do today is to find a way to find dy dx directly from the original equation. In other words, having an equation linking x and y in which we are sure that y is defined implicitly as one or more functions of x, we seek to find dy dx from the original equation. We don't want to solve for y first explicitly as a function of x. Here we do have the option. We could solve. However, as we'll see later in the videotape, we can have equations involving x and y where y is defined implicitly as a function of x, and yet we cannot first solve for y directly as a function of x. So we want to be able to find dy dx while the equation is still in this form. This is known as implicit differentiation. The differentiation we have been doing already, we could think of that as explicit differentiation. Y is given to you explicitly as a function of x. Y equals some function of x, and then we look for dy dx. Implicit differentiation, we start with an equation involving, say, x and y, and y is defined implicitly as one or more functions of x, and we want dy dx, but we do not want to first solve for y in terms of x. Okay. Now, keeping that in mind, let's review some facts about differentiation. If we want to take the derivative of x to the nth power with respect to x, we know that that is nx to the n minus 1 power. Okay? The power times x to the 1 less power. Now, suppose we want to take the derivative of y to the n with respect to x. Now, remember, in a problem like this, y is really a function of x. Okay? It may not be written explicitly, y equals some function of x, but we understand that y is some function of x. So when you're differentiating y to the nth power, you really should be following the rule for differentiating a function of x to the nth power. If you want to differentiate a function of x to the nth power, we know that that is equal to the power times the function to the 1 less power times the derivative of the function. Power, function, 1 less power times the derivative of the function. This is the power rule, which comes from the chain rule. So if we think of y really as a function of x, then the derivative of y to the n with respect to x should be n y to the n minus 1 times the derivative of y with respect to x. In other words, if y is going to be treated as a function of x, the derivative of y to the nth power, it's like a function of x to the nth power, will be the power times the function to the 1 less power times the derivative of the inside, but the derivative of y with respect to x, that's just dy dx. So if we treat y as a function of x, we don't know y explicitly as a function of x, but we have to treat it as a function of x. Then the derivative of y to the nth power with respect to x will be ny to the n minus 1 dy dx. These two key rules will help us in our implicit differentiation. Now let's go back to the problem that we started with. X squared plus y squared equals 4. We would like to find dy dx without first solving for y in terms of x. Okay, the procedure is as follows. We will take derivatives of both sides with respect to x. The derivative of x squared plus y squared with respect to x equals the derivative of 4 with respect to x. Now, we took the derivative, we started with this equation, we took the derivatives of both sides with respect to x. The derivative of a sum of two functions is the sum of the derivatives of the individual functions. So we will write this as the derivative of x squared with respect to x plus the derivative of y squared with respect to x equals the derivative of 4 with respect to x. Now, the derivative of x squared with respect to x. Let's go over here. And let me remind you, the derivative of x squared with respect to x will be just 2x to the first power, or 2x. However, the derivative of y squared with respect to x will be 2y to the first power dy dx. So, over here, the derivative of x squared with respect to x is 2x. This is something, of course, we knew before. The derivative of y squared with respect to x, with respect to a different variable, where y is assumed to be a function of x, we do this by the power rule. So, it's power function to the 1 less power, we don't have to write the first power, times the derivative of the inside. Okay, so for x squared's derivative with respect to x, that's 2x the way we've been doing it. But when it says y squared with respect to x, remember y is to be treated as a function of x, so we do it by the power rule. Function to a power, so it's power, function, 1 less power, times the derivative of the inside. Equals the derivative of 4 with respect to x, the derivative of a constant, of course, is 0. Now, we're looking for dy dx. So get the terms of dy dx on one side and all the other terms to the other. So here, let's say 2y dy dx equals minus 2x. We're going to try to solve for dy dx. 2x plus 2y dy dx is 0. We subtracted 2x from both sides. And now finally, we want to get dy dx alone, so we'll divide both sides by 2y. We'll get rid of it here, and we will have dy dx is equal to minus 2x over 2y. We can divide top and bottom by 2 or cancel the 2, so we get minus x over y. So we have started with this equation involving x and y, and without first solving for y in terms of x, we were able to find dy dx. Okay, now there is one slight drawback in that dy dx is not strictly in terms of x. When we have y defined explicitly as a function of x, dy dx is also given explicitly as a function of x. Here we have dy dx in terms of both x and y. Okay, but we'll see in a later problem that this really will not cause us too much difficulty. Because, for example, if we're trying to find the slope of a tangent line at a certain point, which means we want to evaluate the derivative at a certain point, then we know, not only do we know the x value of the point, we know the y value of the point. So practically speaking, this should not cause us too much trouble. Okay, let's try another example. This time, we'll start with x to the fourth plus x cubed y squared minus 10y cubed equals 0. X to the fourth plus x cubed y squared minus 10y cubed equals 0. Okay, now let us assume that this equation defines y implicitly as a function of x. Okay, we do not want to first solve for y in terms of x, and in fact we wouldn't be able to do that directly. Yet we want to find dy dx. Okay, so we're going to be using implicit differentiation. Remember, our problem here is to find dy dx if y is defined. We have this equation here. Okay, following the procedure we used before, we will take derivatives of both sides with respect to x. So the derivative of x to the fourth plus x cubed y squared minus 10y cubed with respect to x is equal to the derivative of 0 with respect to x. Now the derivative of a sum is equal to the sum of the derivatives of the individual functions. So we will write this as the derivative of x to the fourth with respect to x plus the derivative of x cubed y squared with respect to x. Okay, we can say either plus the derivative of minus 10y cubed with respect to x, or we could have pulled the minus 10 out in front, because a constant can be pulled out in front of the derivative symbol, equals the derivative of 0. Now, the derivative of x to the fourth with respect to x is, of course, 4x cubed. Plus. Now here we have a problem. We have the derivative of x cubed times y squared. This has to be treated as a product. The derivative of a product is the first x cubed times the derivative of the second y squared with respect to x plus the second y squared times the derivative of the first. Okay, in other words, the derivative of x cubed y squared appears in two terms here. Okay, the derivative of minus 10y cubed, let's pull the minus 10 out in front. Minus 10 times the derivative of y cubed with respect to x equals the derivative of 0, which is just 0. The derivative of a constant is just 0. Okay. Now, let's go over what we did. The derivative of x to the fourth we knew right away was 4x cubed with respect to x. The derivative of 0 was 0. For the derivative of minus 10y cubed, we pulled out the minus 10, the constant in front, and said minus 10 times the derivative of y cubed with respect to x. The hard part was here. We had x cubed times y squared. That has to be treated as a product. Okay? So the derivative of x cubed y squared with respect to x is the first function, x cubed, times the derivative of y squared with respect to x, plus the second function, y squared, times the derivative of x cubed with respect to x. Okay, let's see what we get. 4x cubed plus x cubed times the derivative of y squared with respect to x. Now remember, the derivative of y squared with respect to x will be 2y to the first dy dx. Derivative of y squared with respect to x, so that's 2y to the first power dy dx, plus now y squared times the derivative of x cubed with respect to x, which is just 3x squared. X to a power with respect to x, when we do the derivative, that's the traditional way, nx to the n minus 1. However, when we have y to a power with respect to x, we want the derivative, we have to go power times y to the 1 less power times dy dx. Don't forget to throw in the extra dy dx. Okay, minus 10. Now, the derivative of y cubed with respect to x, since it's y cubed with respect to x, it'll be 3y squared dy dx equals 0. Okay, let's rewrite this. We have 4x cubed plus, this is a little awkward, x cubed 2y. Let's write 2x cubed y dy dx. Okay, it seems more convenient to put your constants first and then your variables in alphabetical order. So instead of y squared, 3x squared, we'll write 3x squared y squared minus 30 y squared dy dx equals 0. Now, we want to solve for dy dx. So what we're going to have to do is to get all the terms with dy dx on one side and everything else on the other. And then we will factor out a dy dx and solve for dy dx. So let's see. This term has a dy dx. This term has a dy dx. Those two terms I'm going to keep here, and I'm going to transpose the other terms. That is, I'm going to subtract 4x cubed from both sides, so it appears on the other side, and subtract 3x squared y squared from both sides. So I will be left with 2x cubed y dy dx, I'm keeping that, minus 30 y squared dy dx equals, and now I'll have minus 4x cubed and minus 3x squared y squared. Okay, I kept the two terms with dy dx on the left side, and I transposed the other two terms to the other side. So this appears as minus 4x cubed on the right side. This appears as minus 3x squared y squared on the right side, which is what we have here. Now we want to solve for dy dx. That's our goal. It says find dy dx. Okay, so let's factor out. Every term on the left has a dy dx in it, so let's factor out dy dx on the left side, and we have 2x cubed y minus 30y squared times dy dx. I factored out a dy dx from these two terms, leaving me with 2x cubed y minus 30y squared times the dy dx equals minus 4x cubed minus 3x squared y squared. And then finally, I'm going to divide both sides by 2x cubed y minus 30y squared. To get that dy dx equals that. Okay, so the final answer is that dy dx equals minus 4x cubed minus 3x squared y squared over 2x cubed y minus 30 y squared. Okay, let's go through that one more time. We had to find dy dx. Y was not given to us explicitly as a function of x. So instead we used implicit differentiation. We took derivatives of both sides with respect to x. On the left side we had several terms, but we knew the derivative of a sum was the sum of the derivatives of the individual terms. And we were able to work directly here and here. The middle term, remember, was a product. We needed the product rule, so the derivative of the middle term split into two terms. Then we kept everything with dy dx on one side, brought everything else to the other side, factored the dy dx out on the left, and then divided by what's multiplying dy dx to get dy dx alone equal to whatever we have here. For our next example, let's try the following. Find an equation of the tangent line to the hyperbola 4x squared minus 9y squared equals 36 at the point 5, 8/3. Try to make a sketch of the problem while I'm erasing the board. All right, we have a hyperbola here. Let's see. If y is 0, what are the x-intercepts? 4x squared equals 36, x squared equals 9, x equals plus or minus 3. If you're looking for y-intercepts, if x is 0, y squared is minus 4, and you cannot solve for y. There are no y-intercepts. The hyperbola is one that's opening left and right. Basic shape like that. And there's a point 5, 8/3 on the hyperbola, which would be about here. And we're looking to find the equation of the tangent line to this hyperbola at this point. So we're looking to find this the equation of this line. This is the tangent line that we are seeking. Now we know the point-slope form of the equation of a line is y minus y1 is m times x minus x1. This gives us an equation of a line through the point x1, y1 through the point x1, y1 with slope m. So if we could find a point on the line and the slope of the line, we could write the equation of the line. Okay, well, we have a point on the line, point 5, 8/3. So the answer to the problem, the equation of the line, will have the form y minus the y-coordinate of this point, 8/3, is the slope times x minus the x-coordinate of the point. Y minus the y-coordinate, 8/3, it will be the slope of the tangent line times x minus the x-coordinate. Okay, now what goes in here? Here we have to put the slope of the tangent line. But the slope of the tangent line at this point is simply the derivative evaluated at the point 5, 8/3. So if we could find the derivative over here, dy dx, and evaluate it at the point 5, 8/3, that would give us the slope of this tangent line. And we would know point and slope. We'd be able to write the equation of the tangent line. So all we have to do is fill in what the derivative is at the point 5, 8/3. But let's look at the equation. We need to find dy dx if 4x squared minus 9y squared equals 36. Y is not given to us explicitly as a function of x. So we're going to use implicit differentiation. We will take derivatives of both sides with respect to x. So the derivative of 4x squared minus 9y squared with respect to x equals the derivative of 36 with respect to x. This can be written as the derivative of 4x squared with respect to x plus the derivative of minus 9y squared with respect to x equals the derivative of 36, of course, which is 0 with respect to x. Well, the derivative of 4x squared with respect to x is simply 8x. The derivative of minus 9y squared with respect to x would be minus, it's plus, minus 18y times dy dx equals 0. Okay, I've done in one step rather, what we did last time in 2 steps. It's really minus 9 times the derivative of y squared, but minus 9 now, the derivative of y squared with respect to x is 2y dy dx. So it's minus 9 times the 2y dy dx to give us the minus 18y dy dx. Okay, 8x equals 18y dy dx. You can bring the terms with dy dx to the right side instead of keeping them on the left. Here it seemed easier because I could eliminate the minus sign. And now divide both sides by 18y so that I get that dy dx is 8x over 18y. dy dx is 8x over 18y, or 4x over 9y. Now we're interested in dy dx evaluated at the point 5, 8/3. Remember earlier in the tape when I said having dy dx in terms of both x and y is really not a catastrophe. Because, for example, in a problem like this, when we're trying to find the slope of the tangent line, we know both the x and the y coordinates of the point. So we will be able to evaluate this at this point. We get 4 times x over 9 times y. Now, x is 5, and y is 8/3. So we get 20 over, now 3 goes into 9, 3 times 8 is 24. So 20 over 24, or dividing numerator and denominator by 4, we get 5/6. Dividing the top by 4 and the bottom by 4, 5/6. So now that we have dy dx at the point 5, 8/3 to be 5/6, we substitute that in over here, and we have an equation of the tangent line that I've drawn over there. Remember, we needed point and slope. We were given the point on the line. We needed the slope of the tangent line, but the slope of the tangent line was the derivative evaluated at the point 5, 8/3. Okay, once we found dy dx by implicit differentiation, we were able to substitute in the point 5, 8/3 and find the slope of the tangent line in question. Turned out to be 5/6, and that's what we substituted in here. Let's find dy dx if xy equals x squared plus y cubed to the 5th power. Okay, we cannot solve this for y explicitly as a function of x. Don't make the mistake of thinking you just have to divide by x. That'll have y alone here, but you'll also have y on the right side. Okay, so we do need the implicit differentiation here. We're going to take derivatives of both sides with respect to x. Now, on the left side, we have, once again, a product. To take the derivative of xy with respect to x, it will be the first x times the derivative of y with respect to x plus the second y times the derivative of x with respect to x. First times the derivative of the second plus the second times the derivative of the first. On the right side here, we have a function to a power. To differentiate that, it will be the power times the function to the 1 less power times the derivative of the inside. We need the derivative of x squared with respect to x plus the derivative of y cubed with respect to x. The derivative of x squared with respect to x, of course, is 2x. And the derivative of y cubed with respect to x is 3y squared dy dx. Don't forget the dy dx. When you're doing x to a power, its derivative with respect to x, you just go power times x to the 1 less power. But when you're doing y to a power, its derivative with respect to x, it's the power times y to the 1 less power times the derivative of y with respect to x. Let's see what we have. We have x times, now, this is derivative of y to the first power, which would be 1y to the 0, or 1 dy dx. Now, this is not surprising, because this says the derivative of y with respect to x. This is just dy dx. Plus y times the derivative of x with respect to x. Derivative of x to the first power with respect to x is just 1. Equals 5 times x squared plus y cubed to the 4th power times 2x plus 3y squared dy dx. Now, we want to solve for dy dx. We have dy dx on the left side and also on the right side. What we have here is really a problem in algebra. The calculus, basically, we've gone through already. Now we have to algebraically be able to solve for dy dx. What we have to do is distribute this through the parentheses here. That'll give us one term without dy dx and another term with dy dx. Then we'll be able to deal with this the way we worked in the other problems. So on the left side, we have x dy dx plus y. And on the right side now, we're going to take this. Think of this as a times b plus c. So it's going to be a times b plus a times c. A times b. 5 times this thing to a power times 2x. So 5 times 2x, that's 10x. It'll be 10x times that thing to a power. So it's 10x times x squared plus y cubed to the 4th power plus now we have to multiply this times the 3y squared dy dx. So it's 5 times this thing to a power times 3y squared dy dx. The 5 times the 3y squared, that's 15y squared times the thing to a power times dy dx. So 15y squared times x squared plus y cubed to the 4th power times dy dx. Okay, once again, we had on the left side x dy dx plus y. On the right side, we had this times this plus this. We're going to distribute this quantity through the parentheses. 5 times the thing to the power times 2x gave us 10x times the thing to a power, plus 5 times the thing to a power times 3y squared dy dx. We took the 5 times the 3y squared, that was the 15y squared, and the thing to a power, and then dy dx. So that's what we have. Now we want to solve for dy dx. We want to get everything with dy dx on one side of the equation, everything without it on the other side. Okay, let's make the left side our dy dx side. We have x dy dx here. Let us subtract this term over here. Bring that to the left side and bring the y to the right side. So we'll have x dy dx minus 15y squared times x squared plus y cubed to the 4th dy dx equals 10x, that's already on the right side, times x squared plus y cubed to the 4th minus y. Okay, you can copy that and then we'll go over this. This term stayed here on the left side. This term stayed on the right side. And we interchanged the remaining two terms. In other words, the plus y appeared on the other side with the minus sign, and the 15y squared term comes over to the left side with the minus sign. Okay, so the terms of dy dx are now on the left side. Factor dy dx out from those two terms. Dy dx times x minus 15y squared times x squared plus y cubed to the 4th equals 10x times x squared plus y cubed to the 4th minus y. And now finally, to solve for dy dx, we will divide both sides by this x minus 15y squared times x squared plus y cubed to the 4th. And over here, x minus 15y squared times x squared plus y cubed to the 4th. Okay, we divided both sides by this. Of course, this cancels, and we have dy dx alone on the left side equals 10x times x squared plus y cubed to the 4th minus y over x minus 15y squared times x squared plus y cubed to the 4th power. So we're able to find dy dx without solving first for y in terms of x, using implicit differentiation. And that brings us to the end of this tape.